So on induction motors, these are another type of AC machines, which are also called asynchronous in the sense that the speed of rotation of these machines is not equal to the synchronous speed. So it could be, it is for the motors, it is under the synchronous speed actually, and the speed depends on the load. How much your load is there connected to your machine. It can determine basically how the speed of the machine can change. But in terms of construction, they're similar to other AC machines in the sense that, or other types of machines in general, in the sense that they have a stator and a rotor. The rotor can be of two major types: squirrel cage type, which is the most common, simple and robust. These are basically some bars that have been added and shorted out on the two sides throughout the rotor, and they provide a very the most common type of basically induction motors. However, there is a wound type also, which provides basically external windings that are connected to the rotor in order to be able to change the rotor's resistance for different purposes that we will be covering later. However, in both types, the design is such that the air gap between the stator and rotor be minimal so that you can maximize basically the flow of power through the machine. And these are some schematics that is in the book associated with different types. Now, let's again go back to this formula of N synchronous is equal to 120 times of Fe over P, where Fe is the frequency of the line, and P is the number of poles in the machine. N synchronous is called the synchronous machine, the rotational speed in RPM, in which your rotating magnetic field rotates. This speed would be the speed in the case of your synchronous machines, but not the speed that you have in your asynchronous or induction machines. In fact, there is a difference between the actual speed of the machine and this synchronous speed, which can define the slip, which we will be covering in a bit. Now, basically, the whole concept of the operation of this machine is based on the electromagnetic induction from stator to the rotor. So let's deal with the motors, induction motors. When three-phase currents are flowing through the stator, they will create a rotating magnetic field, which we saw that, right? Speed of that rotating magnetic field would be based on equation 7.1. And this rotating magnetic field will induce a voltage in the rotor. Since the rotor is shorted or is basically closed, it will also result in a current. So the induction of the voltage would be based on the Faraday's law, and this happens on the rotor. Since rotor is shorted, that voltage will result in a current. And the voltage that is induced in a given bar in the rotor can be found through this basic equation that we have covered in the past. Now, we want to see what happens next. Because of the current that flows on the rotor, there would be another field associated with the rotor, another magnetic field, which would be created because of the rotor. Now, the interaction between this rotating magnetic field and the magnetic field associated with the rotor, the interaction between these two will cause basically an induced torque based on these equations, 458 or 460. These are basically the same. So keep in mind that we have a stator field that is because of the rotating magnetic field. We have a rotor field because of the current that flows in the rotor. These two together, these are vectors. When we add them together, that becomes B net. That becomes B net. Now, tau induced can be explained mathematically through K times BR cross-produced by BS, or the same K times BR cross-produced by B net. They're both equivalent. That K is a constant. So let's look at it in here. We have on part A of this figure, we are having a rotating stator field, BS, which is rotating with this speed omega, while meeting basically the rotor bars. It induces a voltage in them. In part B, we have the rotor voltage produces rotor current flow. So that IR is showing basically the flow of current or the phasor of the current that exists in the rotor. Now, using the right-hand rule, if you put your thumb finger in the direction of IR, the rest four fingers will show the direction of BR, which would be something like this in part C. So we have a BS, the stator rotating magnetic field, or in other words, because when I say stator rotating, stator is static, right? Physically static. But the rotating magnetic field is caused by the flow of currents that are in the stator. So let's say BS is that. And then we have IR flowing the current that flows in the rotor. Because of that, we have BR, the magnetic field in the rotor. These two together become B net. So B net is the vector sum of these two. And we have basically angle of theta R, which is the angle between IR and ER. What is ER? ER is the voltage that is produced or induced on the rotor, which is on the same direction as the B net. So ER phasor and B net would be on the same, basically, direction. But this IR would be 90 degrees ahead of this BR with respect to the counterclockwise rotation. Now, if you want to represent tau induced based on equation 460, which is KBR B nets, and the sign between those, this delta would be the sign of the angle between BR and B net. This is now BR, this is B net. So this angle is called delta between BR and B net. This angle, theta R, is called power factor angle on your rotor, right? The angle between the voltage and the current on the rotor. This is the power factor angle in the rotor. And what is the relationship between delta and theta R? This was delta. Delta, how much is this? This is 90 degrees, right? 90 plus theta R becomes equal to delta. So keep that in mind. All right, now, so this was the fundamentals associated with how this torque is produced. That's because of the interaction between the stator and rotor magnetic fields, or the stator and the net magnetic field. And the net magnetic field is caused by the sum vector of the rotor and stator magnetic fields. Now, let's go to rotor slip. We mentioned that there is basically difference between the speed of the rotor and the speed of the stator. Why is it that? So based on this, if BR and BS, if BR and BS are aligned, what happens? This tau becomes 0, right? That's because there would be no relative speed. No relative speed between the stator and rotor magnetic fields. If there is no relative speed, there would be no voltage induced, right? So that's why. So therefore, we never reach the synchronous speed. There would be always some difference between the actual motor speed and the synchronous speed, and that can be described as slip or by slip. Slip would be n synchronous minus nm over n synchronous. If you multiplied that by 100, that will be shown in percent. So why slip exists? If the rotor were to spin at synchronous speed, there would be no relative motion. Consequently, there would be no EMF produced. Therefore, no current, therefore no torque. So thus, to induce current and produce torque, the rotor must lag behind the rotating magnetic field, which will create this slip. All right, now let's look at the characteristic of slip. At startup, when there is no motion, obviously Nm is 0, right? Under those circumstances, the slip would be 100% or 1. Let's go back here. If there is no motion, the slip would be 1, n-sync over n-sync. So we're talking about the two extremes, if there is no motion at all. If the motion is such that it's equal to the synchronous speed, then obviously slip would be 0, right? Which we will never reach that. That's the extreme. We will never reach slip equal to 0. But at no load or very light load conditions, the slip would be very small, around 0.5% to 2%. But as we're increasing the load at full load, typically a slip will basically increase to 2% to 6%, again, depending on the design. In some designs, by their nature and the physical characteristics of the machine, the slip is less, or it can go up to 6% as well. Now, we mentioned that there would be a voltage induced on the rotor and the current flowing in the rotor. That current has an alternative nature itself, but its frequency is different from the frequency of the voltage and current on the stator. The stator's frequency is equal to the line frequency, 60 hertz. But the frequency of the voltage and current in the rotor will not be equal to that. It would be equal to S times the slip times the frequency of the line. Okay? So let's put that in perspective with what we had in here. If there is no motion on the rotor, or if we lock the rotor, if we do not allow the rotor to move, if we lock it, then the frequency of the voltage and current in the rotor would be the same 60 hertz. Under those circumstances, this formula works, right? S times Fe, obviously S is 1, times Fe, that becomes 60 hertz. On the other extreme, if we are rotating with the same speed as the rotating magnetic field, slip would be 0, which means that the frequency would be 0. And that makes sense, right? The frequency would be 0, and if we ever reach that position, which we won't physically, the voltage would be a direct voltage, okay? Because its frequency is 0. Okay, so slip is a design feature, really, not a flaw. So that's part of the nature of how this machine is working. It allows torque production and dynamic response to changing loads. And control of a slip is a key in speed control and torque optimization in variable speed drives. So variable speed drives are basically devices that are based on power electronics, that through them we would be able to have a flexible range of, a wide range of operating characteristics. So, for example, in electric vehicles, we must have this because we want different amounts of torque and speed. We want to be able to control them in a way that would be really reliable and works for us for the purpose of the application of electric vehicles, basically. Let's look at example 7.1. So we have a 208 volt, 10 horsepower, 4-pole, 60 hertz, Y-connected induction motor with full load slip of 5%. We want to see what is the synchronous speed of the motor. The synchronous speed is obviously found through the frequency and P. It's 120 F over P. That becomes 1800 RPM. Part B, what is the rotor speed of this motor at the rated load? At the rated load, we should have how much? 5% slip, right? The rotor speed can be found through this 1 minus S. So through the slip equation, you can find an M, right? If you have the synchronous speed and if you have the slip, you can solve it for an M. And this is what's been done in here. So under full load conditions, we would drop the speed to 1710 RPM. Part C, what is the rotor frequency of this motor at the rated load? So obviously the slip times the line frequency, that becomes 0.05 times 60 hertz, 3 hertz. So the amount of basically frequency in the rotor is just 3 hertz, very small. Alternatively, the frequency can be found from equation 7.9. Yeah, so that's the same thing. 3 hertz. And part D, what is the shaft torque of this motor at the rated load? So the torque is found from the output power over the mechanical speed, right? Omega n. So the output power at rated conditions is 10 horsepower, so 10 times 746. That becomes in watts. And then you have your full load speed, which is 1710 RPM. You multiply that by 2 pi over 60 to make it in radians per second, so that you can find tau load in Newton meters. And there is a conversion to English units as well in pound feet. All right, now let's look at the equivalent circuit of this motor. So we saw that the whole base of operation of this induction motor was because of the induction of some voltage from stator to rotor. So this is very much similar to the action that happens in transformers, right? The difference is that while this induction is happening and we are allowing the rotor to rotate, it starts rotating. So that's the only difference. We are allowing, intentionally designing the machine in a way that we allow the rotor to rotate. So because of that, there would be some rotation in addition to the transformer action involved. So we can use the same concept here to derive the equivalent circuit of the machine using the transformer operation principles. So that's how this is done. So let's start here. On these bullets, an induction motor is operating based on transformer action using induced voltage and currents in its rotor circuit caused by the stator's magnetic field. The induction process is similar to how a transformer is operating. On the stator, we have the primary windings, as if on the rotor, we have the secondary windings. Because of this similarity, the equivalent circuit of the induction motor can be similar to that of a transformer. However, because the speed of the machine can change, the effective turns ratio would be a variable turns ratio, right? The equivalent circuit of an induction motor is derived from the transformer model. So we started from the transformer model. In a transformer model, and hence in here, we have two sides, primary, secondary. The primary would be your stator, the secondary would be your rotor. On the rotor side, you have basically a resistance and a reactance. That reactance is associated with the rotor. That resistance is the rotor's resistance. And we are shorted. This is associated with the squirrel cage induction motor, right? So we are shorted on the rotor side. On the stator side, we have this R1 and X1 resistance and reactance. And we are also having the RC and XM, which are representing the magnetization part, how magnetization happens, how the field in the stator is basically created. And RC is representing basically the core losses. Okay. Now, we know that on the rotor side, we could have a variable frequency. Isn't that so? And because we have a variable frequency, could change depending on how the slip is changing, therefore that XR would not be a constant value. That XR, the reactance, always depends on how much frequency is there, right? So we should keep that in mind. Also, ER, the voltage that is on the rotor, that is also a variable voltage, because it changes as the slip is changing. If the slip is 1, that we would have the maximum voltage induced. If the slip becomes 0 or close to the synchronous, the machine rotates close to the synchronous speed, then the voltage would be minimized, or 0, ideally, or in its extreme. So let's put that in perspective. ER can be represented, the voltage on the rotor, induced on the rotor, can be represented with respect to the voltage under locked rotor conditions. So if you lock the rotor and you call the voltage that is induced on the rotor ER0, then with respect to that ER0, ER can be defined as S times ER0. If S is 1, locked rotor conditions, ER0 would be the same as ER. If S is 0, then ER would be 0, which makes sense. And keep that in mind that FR is also equal to S times FE. FR is the frequency of the current that is flowing on the rotor side. And XR, the reactance that we just mentioned, is L times omega on the rotor side, which would be FR. And FR is S times FE. So we can also represent the reactance on the rotor side as with respect to the reactance on the rotor side under locked rotor conditions. So if you call XR0 as the reactance of the rotor under locked conditions, then S times XR0 becomes X, right? So why we're doing this, that's because we want to simplify this diagram because of its variability with the slip and all of that. We want to make it as simplified as possible. So in the next stage, and in order to produce a per phase equivalent circuit, we refer everything from the rotor side to the stator side to just remove that transformer portion. We don't like that. So we do it like this. We remove that, transfer basically XR and RR to the stator side, call them X2 and R2 over S. Now, this is basically how the variability of the slip can show itself in the equivalent circuit. That's in here, only in here. That E1 doesn't change with voltage. It changes with voltage, but to basically a small extent, because these two impedances are one next one or another. So that basically nothing is dependent on the frequency in here, not even on X2. So not even on X2. The only part that changes with the changes of slip and the frequency on the rotor would be now R2 over S. Now, these are the equivalent, basically, representations. R effective is defined as E1 over ER0. What is ER0? ER0 is the voltage here under blocked rotor conditions. So this voltage E1 over ER0 is called A effective. And with respect to that A effective, these R2, X2 components are defined. So R2 would be A effective times squared, and A effective squared times RR. And X2 would be A effective squared times XR0. All right, and then, and E1 here would be the same as ER prime. ER prime is nothing but ER, which has been transformed or transferred to the stators. So all based on transformer relationships. So this would be basically the equivalent circuit that we use. And we're supposed to be given all of these parameters, R2, X2, RCXM, R1, and X1 associated with a motor. And based on that, we can come up with different types of calculations. So when you are attaching your motor to external source, this is basically the equivalent impedance that you're watching from the terminals of your motor. And that equivalent impedance is not constant. Why it's not constant? Because of S. S is the only term here that makes the equivalent to be variable, to become variable. Looking at the flow of power, or the power flow diagram, on the left-hand side here, we have P in, which is the electric power that we're giving to the motor from its terminals. Then we would be basically having the SCL, or stator copper losses, that are represented by this R1. Then we would have the core losses, which would be represented with this RC. Here, we call the power after these losses the air gap power, the power that is existing on the air gap right between the stator and the rotor, or PAG, P air gap power. Now, after the air gap power, so it's here, the power that is received at this point. And then after that, we have another term that loses power, and that would be the rotor, which we call it the rotor couple losses. And then we reach basically here, which we call the power at this point, the converted power. Now, in order to show that in a better way, we can basically write this R2 over S in two terms. So here you can see that R2 plus R2 times 1 minus S over S, that becomes R2 over S. So these two would be equivalent, basically, circuits, right? These two would be equivalent. The only basically difference is that this better represents the copper losses that are associated with the rotor, and this better represents the converted power. So the power that is lost in this variable resistance would be equal to the converted power, the power that is given to your load, that is going to be given to your load, but after that you have some mechanical and rotational losses that would be extracted. So this is the converted power. You have the, which is equal to tau induced times omega m. You have the friction and stray losses, all of these losses that are miscellaneous, plus the friction losses associated with the friction of the mechanical parts together and mechanical parts and the air. All of those subtracted would be giving you the output power now, which is tau load, the applied basically torque to the load times omega m. So the difference between tau induced omega m and tau load omega m is because of the difference that is happening because of the friction losses plus the stray losses. Let's look at these losses in terms of the parameters. So PSCL, or the stator couple losses, is 3 times R1I1 squared. The 3 is coming because of the three-phase factor. P core would be 3E1 squared times GC. And what is GC? GC is 1 over RC. And then we have PAG, the air gap power, the power over here, would be the input power minus the stator copper losses minus the core losses. That becomes the P air gap. This P air gap is also equal to 3 times I2 squared times R2 over S, because there is no loss of power in X2, right? Therefore, air gap power can be also represented as this equation 728. The rotor copper losses would be 3 times R2 I2 squared. And the converted power, the power that would be here in your resistance in here, would be 3 times R2 I2 squared times 1 minus S over S. The converted power can also be shown in terms of 1 minus S times P air gap. So these are, depending on what you have, might come handy. The output power would be the converted power minus friction and windage minus miscellaneous powers that are extracted here. And we have tau induced, and tau induced equal to P converted over omega M, or PAG over omega S. So this is very useful sometimes. The induced torque would be the air gap power over omega synchronous. Since omega synchronous is a constant, it only depends on PAG. However, if you want to represent tau induced in terms of P converted over omega M, both of those P converted and omega M would be variable terms, right? So sometimes in your calculations, it's much easier to use these 736 instead of 735. We have a 480 volt, 60 hertz, 50 horsepower, three-phase induction motor, which is drawing 60 amps at 0.85 lagging power factor. The stator copper losses are 2 kilowatts, and the rotor copper losses are 700 watts. The friction and windage losses are 600 watts. The core losses are 1800 watts, and the stray losses are negligible. We want to find out the following quantities. The air gap power first, PAG. So the air gap power, we know to find the air gap power, we use the input power, which is square root of 3 times VTIL cosine of theta. So we have all the information in here. We know how much power is how much current is drawn. And this is basically 480. That's the terminal voltage, line to line. IL is the line current. Square root of 3. It makes the input power to be equal to 42.4 kilowatts. Now, from the input power, you need to subtract the stator couple losses and core losses to find the air gap power, right? So go back here. The air gap power is a power here, which would be found after you have P in minus this loss minus this loss. That becomes air gap power. So since we're given the losses of stator as well as the core, we can find the air gap power easily from here. Part B, the converted power. The converted power was the power that was a difference between the air gap power and the rotor copper losses, right? So that's what happens in here. The air gap power minus the rotor copper losses gives you the converted power. Part C, the output power. The output power would be found from the converted power minus the friction and stray losses. So this gives you the output power. And finally, the efficiency of the motor, which is the output power over the input power. Now, as I said, it's sometimes much easier to separate the RCL, the rotor copper losses, and the converted power in the equivalent circuit. So this R2 over S in here includes both the rotor copper losses and the converted power. But if you rewrite this R2 over S as these two separate resistances, R2 represents the rotor copper losses, and R2 times 1 minus S over S represents the converted. So this is another example. We have a 460 volts, 25 horsepower, 60 hertz 4-pole, a Y-connected induction motor, which has the following impedances. in ohms per phase refer to the stator circuit. So we're given the parameters R1, R2, X1, X2, and Xm. And the total rotational losses are 1100 watts and are assumed to be constant. So we're not given the RC, which indicates that the core losses are negligible or zero, but we're given the rotational losses. Well, it says that the core loss is lumped in with the rotational losses. So it includes basically whatever the core losses is. That is part of this 1100 watts. For a rotor slip of 2.2% at the rated voltage and rated frequency, we want to find out speed, stator current, power factor, P converted, P out, tau induced, tau load, and efficiency. Okay. So we can draw use the same equivalent circuit model and the power flow diagram. To find the synchronous speed, we can find first the synchronous speed, which is 120 F over P, 1800 RPM, or in radians per second. And then having the slip, because we have the slip 2.2%, you can find out the rotor's speed or the actual motor's speed through 1 minus S times N synchronous. So that would be 1760 RPM or 184.4 in radians per second. Now it's asking to find the stator current. So let's go to see how you can find the stator current through either circuits. To find this stator current, what we really need to do is to find out this equivalence impedance, right? And we have everything to calculate that because we have the parameters of the machine and we have the slip. Because we have the slip, then we can find out that equivalent impedance. That equivalent impedance has been found. And we phi over Z equivalent would be that current I1, which is the stator's current. Keep that in mind. This is basically a Y-connected machine. So this 266 is because we divided 460 over square root of 3. This is per phase circuit, right? So the voltage that we need to apply in here is the phase voltage. Phase voltage would be the same as the line voltage if the machine is delta connected. But since it is Y connected, we have to divide that by square root of 3. So we found the stator current in part B. Now we need to find out the power factor. So once you find the current in the stator, and assuming that the reference of angle is on the stator side, that angle gives you practically the power factor angle. So the power factor angle is is the angle of voltage minus the angle of current. The angle of voltage is 0 minus 33.6. That becomes plus 33.6. And that becomes basically a lagging power factor because voltage is ahead of the current. Current is minus. And now it asks for the P converted and P out. So where was P converted? Then go back here. P converted was P air gap minus basically the rotor copper losses. And P air gap was input power minus stator plus core losses. So the input power is found, then the stator copper losses. Therefore, since the core losses was lumped with the rotational losses. So the input power minus the stator copper losses becomes the air gap power. So we're neglecting the copper losses, the core losses here because we don't have any information of that. And then P converted would be 1 minus S times P air gap. This is the equation that is very helpful. Again, if you have the slip already, 1 minus S times P air gap, that becomes the converted power. And the output power would be the converted power minus the rotational losses. Now, tau induced is P air gap over omega synchronous. This is, again, the equation that I said is very useful. If you have the air gap power, since omega synchronous you already had in previous parts, it's easy to find it that way. And the output torque is P out over omega n. So this tau induced can be also found from P converted over omega m. So either of these works. And finally, we have the efficiency, P out over P input, which becomes 83.7. So this is a problem in which the slip was given. So we typically have two types of problem in induction motors. The first one is when you know the slip, and since you know the slip, you can find out the equivalent impedance and come up with the rest of the calculations. Another type of problem is when you have the input basically power, the input power or the input power and power factor, so that you can calculate the complex power on the input. Once you have the complex power on the input, then you will be able to find out the slip. And once you find the slip, you can find the speed, right? So that's another type of problem. All right, so let's talk about the torque and speed a little bit more in detail. In terms of the torque development, the torque is proportional to the product of the rotor current and the magnetic field from the stator. It also depends on the slip, which is the difference between the synchronous speed and the rotor speed. Let's have a physical interpretation in here. So the slip is creating a relative speed between the rotor and the magnetic field. This relative motion induces the current in the rotor and generating the torque. So we discussed that. Here are basically the torque development in two different conditions. So part A of this figure is showing the magnetic field in an induction motor under light load conditions or small load conditions. So this is the stator field or the rotating magnetic field. Since there is small, basically, voltage induced under light load conditions, we are closer to the synchronous speed, right? So the voltage that is induced in the machine is small under light load conditions or no load conditions. Therefore, BR is small. And we have a B net here, which is BS plus BR. The angle difference between the voltage and current on the rotor is very small under light load conditions. That's because S is close to zero, right? S is close to zero. When S is close to zero, we're closer to a DC current and DC voltage. Therefore, reactance would be minimal. When reactance on the rotor is minimal, it means that the voltage and current on the rotor are almost aligned with each other. There is not much angle difference between the voltage and current on the rotor side, okay? Now, I want you to compare that with the conditions that you have, basically, a full load condition. Under full load condition, you can see that slip becomes big. When slip becomes big, there is the angle difference between the voltage and current would be much more because X would be involved now. X on the rotor side would be involved because the slip has increased. The frequency of on the rotor side has increased. So therefore, there would be more angle difference between ER and IR. This angle between ER and IR is called theta R. This theta R in the light load conditions was almost zero, very close to zero, very small. Now, I want you to look at basically the BS, BR. There's more voltage here induced. BR is bigger. But nevertheless, B net would be almost the same. B net here, which is the sum of BS plus BR are almost the same. Why is that happening? The B net is representing the voltage that is being induced on the rotor. What is the voltage that is being induced on the rotor? That's basically proportional to the voltage in here. This voltage, no matter how big or how small the load is, this current goes through R1 and X1 to create that voltage, okay? E1 voltage. This R1 and X1 are small, comparatively small, with respect to, for example, RC and XM. Therefore, this voltage drop would be small. Or in other words, this E1 is almost equal to the terminal voltage in here, VP, or the source voltage. What I'm trying to say that this E1, which is really representing that B net, is remaining almost constant, no matter how much load you have in your system. And remember why we want to use that? That's because the tau, or the electromagnetic torque, was Ka BR times B net, right? Or K times BR B net sine of delta. Now, B net being almost constant, K being constant, this means that tau induced would be dependent on BR times sine of delta. That's what I was trying to reach at. So that's why we're using this representation of tau induced much more with respect to the other representation, because we had two equations. You go back here. We had both of these formulas, KBR times BS or KBR times B net. We're using this more because this B net is almost constant. So therefore, the tau would be mostly associated with BR and the angle that is between BR and B net. All right, let's have a review in here. B net is proportional to IM and proportional to E1. Okay, B net is proportional to this E1 and IM. Tau induced is K times BR times B net, or its magnitude is KBR B net sine of delta. So E1, and hence B net, is almost constant, doesn't vary a lot with load. So the torque would be mostly proportional to BR and delta, which is the angle between BR and B net. This delta is the angle between BR and B net. And delta, we know that it's equal to theta R plus 90 degrees, where theta R is the power factor angle of the rotor. So I should correct that, power factor angle of the rotor, the angle between ER and I. Now, I'm trying to show you this. We're talking about tau induced, which was a function of BR, B net, and the cosine of the angle. So keep that in mind, that sine of delta, because delta is equal to theta R plus 90 degrees, sine of delta becomes equal to cosine of theta R. Sine of delta becomes equal to cosine of theta R. So therefore, all of these components that we're seeing in here, BR, B net, cosine of theta R, these are the components that make the tau. These multiplied together make the tau. Now consider a motor in which you are changing its speed from 0 all the way to the synchronous speed. From 0 all the way to the synchronous speed. We cannot reach the synchronous speed, but this is just for theoretical explanation of the phenomena. So we multiply all these together and we plot tau. We want to see how tau, or the torque, is changing. Okay? Now look at this torque. Here we have the starting torque. The starting torque is the torque when speed is 0, when the motor is not in motion. You apply the voltage. Right at that moment, there would be a tau applied, which you call it the starting torque. When you get to the synchronous speed, the torque would be 0. And that's obvious, because if you are reaching the synchronous speed, there would be no voltage induced, no torque induced. In between, we are rising the torque and reducing the torque as you are changing from the 0 speed to the synchronous speed. So you're rising the torque and then you're reducing the torque. You reach a maximum point, which you call the pull-out torque, the maximum torque in here. So this is the maximum torque that you can create in this machine. Now, we said this tau induced is the product of all these three elements. And B net is the one that is pretty much constant, doesn't change. So one of these BR is reducing as we increase the speed. The other is increasing as we increase the speed. So this tells us that when the torque is growing in this first half part, the cosine of theta R would be the determining factor with respect to this BR. So this is the determining factor, because you see that the tau is overall rising. In that declining portion of the torque, you see that torque is reducing, and for the most part, that's the BR that is the determining factor. Okay? That's the BR that is the determining factor. Note that as the speed is increasing, BR is decreasing, cosine of theta R is increasing. Their product would be sometimes increasing, sometimes decreasing. In this first portion is increasing because the tau is increasing. The second portion is decreasing because the tau is decreasing. Now, this is just an analytical perspective over the torque in relationship with the load. If the load is increasing, if you go back, if you basically go to the left side, when you have less speed, when the speed is reduced, you have more load. When the speed is increased, you have less load, right? Keep that in mind. The speed and torque relationship with respect to the load. Now, let's come up with a torque equation. So in order to come up with a torque equation, here's what we do. We know that torque is equal to P air gap over omega synchronous. We go through this equivalent circuit. We know that in this equivalent circuit, P air gap is 3 times R2 over S times I2 squared. Now, from this, we find a Thevenin equivalent circuit from the rotor, from these two terminals, which gives us this. So we're trying to watch the circuit from these two terminals. So V Thevenin would be found from V phi times the JXM over JXM plus these two. So this gives us the V Thevenin. The Z Thevenin would be basically when you short out this voltage source and watch basically this overall impedance that is watched from here. So this would be the Z Thevenin. Now you have your Thevenin circuit. You combine V Thevenin to R Thevenin, X Thevenin, and then connect the R2, S and X2 again. So basically these two circuits are kind of equivalent in the sense that they provide you with the same conditions. And when you do the math, V Thevenin would be almost equal to this. Your R Thevenin would be almost equal to this, and your X Thevenin would be almost equal to X1. So when you apply these into the torque equation, this is basically the approximate torque equation that we get. So let's see what this torque equation depends on. This omega synchronous is constant. V Thevenin is almost constant, right? V Thevenin is almost constant. R2 is constant. R Thevenin is constant. X Thevenin is constant. And X2 is constant. So for the most part, this tau is changing because of the slip. And the slip changes because of the changes in speed. Now, if you go ahead and plot that tau with respect to speed or slip, you get something like this. So this is basically the induced torque. On the horizontal axis, you have the speed. Speed changes from 0 to n synchronous. In terms of slip, when speed is 0, slip is 1. When speed is n synchronous, slip would be 0, right? So this is the starting torque. This is the pull-out torque. And we are operating the machine close to the synchronous speed here at the full load torque. So this is the torque at full load. If you put basically the power and torque together on the same diagram, so here is the basically induced torque. This one is showing, this side is showing the power. This is the curve of power with respect to speed. And this is the torque curve with respect to speed. Note that at the time that you have the maximum torque, which would be here, you do not have the maximum power, right? So there is a difference between the maximum power point and the maximum torque point. Keep that in mind. Now, let's see how you can find out the maximum or pull-out torque. In a torque equation, all the terms are constant based on what I just mentioned, except the S. So therefore, to find the maximum torque, you can find the derivative of this equation and equalize it to 0. As a result, the S, or the slip at which the maximum torque occurs, would be found based on equation 753, which is depending on R2, R Thevenin, X Thevenin, and X2. And then when you put that slip into this equation, you find the maximum torque. So the maximum torque, or the pull-out torque, would be found based on equation 754. Okay, so again, we get the derivative of tau induced with respect to S, equalize it to 0, find S, that S would be called S max, which means that that is the slip of the machine at which the maximum torque occurs. Once you put that S max into the torque equation, you find the maximum torque as tau max. Now, let's look at this S max. There are some applications where we want that pull-out or maximum torque to happen at the start of the machine. So you have some heavy load conditions, and right at the time that you want to basically apply that torque, that load to the motor, you want to have the maximum possible torque. So you want your maximum torque to happen close to startup conditions, close to the time that your speed is 0 or close to 0. So for that, let's see how the S max is looking. S max means what? Means the slip at which the maximum torque occurs. At the start of the motor, what would be the S? What would be the slip? So when the slip is 1, it means that we are under basically startup conditions. Now, if you want to have your maximum torque happening at the startup, it means that you want your S max to be as big as possible, right? So therefore, increasing R2 to increase the slip at which the maximum torque occurs can be the answer. Therefore, maximum torque occurs at lower speeds when you maximize or when you put that R2 value to be as big as possible. Now, what was R2? That is the rotor's basically rotor's resistance. And look at here, the other components in this equation of S max, R Thevenin or X Thevenin, they do not depend on rotor parameters. Only X2 depends on. So one way to have your maximum torque happening at startup or close to startup would be to maximize R2 or to minimize basically X2. Let's talk about R2 only here. Once you increase R2 and whatever R2 value you put in here, you put that, you find that S max, and you put that S max into this torque equation, and you will find that the torque, the maximum torque, would remain almost constant. So look at this curve. In this curve, you have basically a certain condition where a rotor's resistance is R1. Okay, consider that condition. You get a certain torque versus speed characteristic, and this is going to be your pull-out or maximum torque. Now you increase that resistance from R1 to R2. So R2 is going to be greater than R1. You still get the same maximum torque, almost the same maximum torque, but just happening at a lower speed. You keep increasing the R to R3, and then you get almost the same maximum torque also, but happening at even a lower speed, until you really increase your impedance, your R2, in your rotor to R4 and R5 values. And you can see that as you're increasing the resistance of rotor, you can get the maximum torque happening closer to startup conditions. So that's one strategy that we can use in order to maximize the torque at startup conditions. Okay, so there is an example here where you have a two-pole machine which is supplying 15 kilowatts to a load at a speed of 2950 RPM. We're asking the motor's slip, the induced torque in the machine under these conditions. What will the operating speed of the motor be if the torque is doubled? How much power will be supplied by the motor when the torque is doubled? So I don't want to go into details of this problem because you've been given the same problem in MATLAB as your homework. So under MATLAB, you would need to come up with the same type of solutions that were found in this example. Another example is talking about another motor that is under these rated conditions, and it's Y-connected. Its R1, X1, R2, and X2, and Xm values are given. It wants to find out the maximum torque. So to find the maximum torque, you would need to come up with S max first, S at which the maximum torque happens. It requires basically R Thevenin and X Thevenin values. So R Thevenin and X Thevenin values would be found based on basically what was given in a few slides before. And also you can find V Thevenin, and based off of those, you can find the tau maximum. So this is the maximum torque of the machine at 229 Newton meters. And then the question is asking, what is the starting torque of the machine? So the starting torque would be the torque at which S is equal to 1. right? Where S is equal to 1. This is the torque equation. When you put S equal to 1, you find the startup torque, the torque at starting conditions. So if you do so, you find the starting torque. So the starting torque is 104 Newton meters, whereas the maximum torque is 229. So this torque at startup may not be enough to basically start the load, to rotate the load. So therefore, if you want to increase this startup torque, one way to do that is to increase the rotor's resistance. So part C of the problem is about that. When the rotor resistance is doubled, we want to see the speed at which the maximum torque now happens. So when the resistance is doubled, slip at which the maximum torque occurs would be 0.396, which gives you a maximum torque of 229, which is kind of the same value that you had in here, but at a different slip. So at a different slip. Here, the slip was 0.198. Here, the slip is 0.396, which is closer to the startup conditions. Now, if you, with that doubling the resistance of the rotor, if you want to see what is the torque at start, then you would go back again in this equation with slip equal to 1, but your R2 value has now doubled. So you would be able to find out the starting torque in these conditions. It's here. So the start torque now goes to 170 from 104, which is a higher torque. So you were able to increase the start torque from 104 to 170 by doubling your rotor's resistance. And now it is asking to calculate and plot the torque speed characteristic of the machine, which there's a code given in here, and you've also been provided with a MATLAB experiment as a homework. So you should be able to plot the same torque versus speed characteristics with the original value and the double value of the rotor resistance using that code.